Do you hear me? No. It's okay for recording. I think I'm not going to have any kind of other microphone. It's okay. I need the other one. Okay, no problem. I'm going to talk loud. So, my name is Javier Pimas. I'm going to present some improvements to... What's her? No, the other is for the ambient, he said. I can switch here?
No, it's not a lot.
Ah, okay. Ahí está.
Okay.
Que yo lo engancho.
Ponelo o enganchate en la cinta, pero en el medio ponelo.
Okay? You hear me now? No. Now? Yeah, okay. This is much better. Okay, my name is Javier Pimas. I work for this Armista. I want to thank also Caesar System, which is our, main client. We work for them in Bee Smalltalk. This talk, I did a presentation last year and in Smalltalks in Rosario. I also did one at ISAG. So I have introduced a bit what it's about with Bee. Bee is a big project. It's about making a new kind of Smalltalk. There's a lot of work by Caesar Systems in the image mainly, and we at this Armista are working on the kernel stuff. Our project is to create a self-hosted VM that is written completely in Smalltalk. So I also want to thank Javier Burroni and Gera Ricciardi. The translator is Gera, Javi is there, and so I want to thank them because they started the project. They did all the hard work which I took to continue developing. So thank you. So what did they do and what I extended? First of all, I think I can pass the slide with this. So it's much better. So what did I do? A JIT in Smalltalk, not shit. They didn't do shit, they did JIT. Okay? So they started with that, and then they added what we call under primitive. It's like a meta-object protocol, which allows to access low-level stuff about objects like the header and things like that. They implemented GC with these under primitives, and then we added method lookup primitives and native helpers to that, so that we could implement a self-hosted VM. So how do we wrap all these things together to make a self-hosted VM? I'm going to pass this as fast as I can because the main stuff is about performance, but we did it with objects. Okay, so I prepared this self-hosted VM in 3 little steps. The first steps, what you have to do, how you start with objects. Okay, so what you do is this kind of thing. We have in this Smalltalk, it's a Digitalk derivative. We have libraries, Smalltalk libraries. Okay, so we can pack objects in a very similar way that they are represented in memory when they are loaded. So what we did is a small kernel. In that kernel, we actually have a small object that tells about what the space is. That's why it has a base, it has the limit, and the next free position. We have this small kernel. We place all the objects there. When we start, we create a bigger arena in external memory, and we start placing new objects there. That's the main idea of how we allocate objects and how we place the objects in the kernel. Then we also have to take advantage of the JIT that we are making. Yeah, I'm going to do that every time I say JIT. Okay, so they made the JIT. So GIT. So we took advantage of that, so that we could generate native code for each method in the smalltalk kernel. And how do we represent that native code? We created, we have in compiled methods, we have an instance variable that refers to the native code, and the native code is something similar to the machine code. It's actually an object that points to the machine code, which is stored in a byte array, and also points to the references, tells about the references inside that code. So we can see the native code referencing this byte array, but this byte array is actually native code, and the native code has references to objects in some places, so we have to store that references so that we can modify them, or when we have GC or something like that. Then under primitives. What are under primitives? For example, think on this method. This method is called behavior. It's something similar to the class. It's like similar to obtaining the class or the method dictionary of an object. So what we have to do is think if it's a small integer or if not, and if it's a small integer, take the method dictionary of the small integer, and if not, take the method dictionary array from the header of the object. So what we do is this little basic add 0 that takes actually the slot of the object that is before the first data slot. Okay? So, but how does it work? We tell the JIT that that this special selector has to be nativized with inline assembly. Okay? So we tell the nativizer, when you find basic add, you have to do that thing, convert the parameter, the argument to a native integer, and then access raw memory. Also, the test is a small integer is another special selector. We do the same. With this, under primitives, we can call everything. Okay, anything that was previously in the hosted VM a primitive, now we can call it by mixing under primitives and smalltalk code. Smalltalk code with regular messages. So we added lookup. I don't know if you can read that. It's maybe a bit small, but we just called a method that this is lookup and invoke, which is finding the method that you have to execute given a selector, and then actually invoking it. Okay, it's not the same than only finding the method. So we delegate finding the method to another method that is lookup, and we continue. We have to do a special arrangement because lookup shouldn't do lookup. If it does lookup, it would recursively call itself and never end. So we have a special object that tells the JIT that this special method, this specific method, should be nativized in a different way. Okay, then just let's see another primitive new. Primitive new is a primitive that calculates the size of the object and allocates the amount of space necessary. Okay, I only put this little thing. Then we have what is allocating a space for this kind of object. We have to allocate the space and then initialize the slots. And finally, a primitive for blocks. For example, consider when you have something like detect. Eventually, you are going to call value. So when you call value, you are going to execute this, which only checks the the argument count, and if it's valid, it translates control to the code of the method. Okay? We can see a little bit about code. It takes from the block closure the slot. Actually, it sends method that takes from the block closure the first slot, prepares that method for execution, and then after the method is prepared, fetches the block, the native code of the block, and returns it. So we can do that for all primitives, and with that we can prepare a self-hosted kernel. We have this little library that is the smalltalk-kernel that includes only the main classes and kind of objects that we need for running Smalltalk and for loading other libraries. Okay? So with that, we put it together and apply some magic. Okay? Then some more magic, and we generate an executable file. Well, this magic is just like adding common objects like true, false, adding the lookup, adding an initial space for the arena, some kinds of things like that. So this is actually very small. Very small. I think this executable generated is like between 2 and 4 megabytes, depending on what you put inside it. Yeah, actually, the arena is one of the things, and we have some space for creating for FFI, but it's like that. So we try to be minimal in each step we do. This kernel doesn't include GC, doesn't include JITing, doesn't include the Smalltalk compiler. It doesn't include almost anything. So what do we do? If you can, for example, create your application in a project, you compile it, you generate native code, and then you tell the kernel, you tell the kernel, okay, b.exe, you tell, okay, execute this library. It loads the library, it has its native code, it runs. So you can also ship your library without native code. For example, we can load the JIT. So you can also nativize another more code. For example, suppose you have this method. You want to compile it, okay? So you are going to load the compiler. Pay attention to the compiler that doesn't have any native code. Oh, why? Because if you want to use the compiler, you can load the JIT and nativize the compiler. After you have nativized the compiler, you can compile your method and then nativize your method and execute it. Okay? That's the kind of things we do to be minimal. But okay, so how does it work? Is it fast? Is it slow? What do you think? Yeah, this is fast. There. But this Smalltalk, it depends. Okay? If you do nothing, it's really slow. It's awkwardly slow. It's like crap. So, well, this is a problem in the slide. So, what was the host VM like comparing to the host VM? We have some metrics that are not so good, like slopstones, smopstones, tiny benchmarks, but are okay for now for measuring performance. And so when we started, we were like 700 times slower than the host VM and 2,000 times slower at a higher level. Okay, this is caused because we have a very similar JIT. So the problem is in the primitives and object creation and that kind of things. So that's the main place where we have been focusing. So what did we do? We started, like we said, okay, we want to send a message. We started with method lookup. Why? Because we knew it was slow. and that was all. We said, okay, we are going to start with this without doing anything. Okay, we just close our eyes and beg, hope this is God. I wish it to be a problem of the message lookup, so I'm going to improve it, and let's wish it works better. So the problem is similar. It's simple to understand. You send the message, you give the selector, the receiver. You have a given receiver, so you have a pair selector and class, or selector method dictionary, or whatever. So you want to find the compiled method that will be executed. That's the main problem of lookup, okay? But what were we doing in lookup? We were doing a linear scan of all the hierarchy of the object. We said, okay, we are looking for this selector. Let's look at the first method dictionary, try to find it linearly there. It's not there, okay? Pass to the other. It was very slow. Okay, so the first optimization we did was supporting the monomorphic inline cache that is like this. Is okay, but almost all times you send a message from some site. The next time you send the same message, you are going to send it to the same kind of object. So what you can do is say, okay, in the place where I put the call to lookup, I can say, no, after lookup, I can say, well, now call the native code of the method that you just found, but be careful, you have to go a little back. You have to not jump directly to the code, but add a small stub that says, check the class of the object if it's still the same. That's the monomorphic inline cache. We implemented this. We also implemented a global cache because that was good. That improved performance a lot, but it was really slow. Yet it was slow. So we said, what else can we do? Another kind of optimization for method lookup is global caches. It's a big table where you do a hash, for example, of the selector and the method dictionary array. Okay, with those things, you have only one implementer. So when you do lookup, you hash this, you save the results in the table, and in the next lookup, you go and first, before doing lookup, you go and search in the table. This improved performance even more. After doing this, we were like, I don't know, like between 100 times slower than the host VM, which was a big improvement from the previous one, but it was still slow. What kind of things did we do? We just said, okay, I don't think you can see very good that. So we can run slopstone and smopstone, but these are like benchmarks that measure a lot of things. So we want to focus a little bit more in each primitive. So we split these benchmarks in little pieces. So for example, we could measure what was the time for array creation, or for sending value to a block, or accessing a string, or whatever. With this, we could at least say these kind of things. We run this on the host VM, and we run that on B. So we could compare. Is this going slower because of, I don't know, array creation? I don't know. Maybe yes, because this is 10 times slower. But we have here something that is, I don't know, 100 times slower. So we focus on that. Okay. And what else could we do to improve performance? We said, well, this is a bit dirty, maybe a bit risky, but we can invoke stuff. For example, when you have a monomorphic inline cache and you send a message that is implemented in object, you are going to patch the class check of the method that is executed with one kind of receiver. But this method is generic for object. I don't know, like add. Okay? So the next time you send add to another object, it's probably going to be of another kind, so the monomorphic inline cache will fail. And the same happens to methods implemented in class, because each object of different classes, when you execute a method on the class side of the object, you are going to fetch a different meta class for each object. So you have the same problem. This kind of places are bad for monomorphic inline cache. And so instead of doing lookup, we can just invoke. I'm going to give some examples. For example, just remember that the methods that we are talking about are very primitive-like. So for example, consider the implementation of add. Okay, we check if it's a small integer, and then we check if it's a kind of bytes or not, and we send another message. We delegate to basic byte add or basic object add. Okay, we are just delegating like if we were programming anything. But if we send add to two different kinds of object, the class check will fail many times, and that's the problem. So we can say, okay, basic byte add is a method that is going to be always the same anywhere when you send basic byte add. We can just invoke a compiled method that we are going to tell you which it is. So again, we configure the JIT, but to do this kind of invokes in many methods. There are not so many. I don't know, like 20, not much. So, but even doing this, we got even better performance, while we were still not happy. Like, I don't know, maybe being 40 times slower, we are still slow. So what else did we do? We said, okay, we might want to write a new compiler just to optimize these cases of the primitives I showed. I have shown one. For example, this kind of thing, it's a smalltalk code, it's JIT, but it could be faster. If you compile it with a standard jitter, it's going to be fast, but we could make this faster. And if we are invoking methods, because basic byte add is going to be invoked, so we could inline that method instead of invoking it. So we thought, okay, let's try making a compiler. This is an SSA-based compiler. It doesn't support, it's very simple. Even if it has many passes, it tries to be very simple. For example, it doesn't allow for compiling loops. If you want to compile a loop, just use the regular compiler. For now, it's not possible. Maybe tomorrow we'll add support for that. We don't care now. So what we do is we just convert the AST to an intermediate representation. After we convert into this intermediate representation, we try to lower the level of these pseudo instructions and lower it and lower it and lower it until we are in a place where we can allocate register for the instructions and then assemble that. And with that, we got even more performance benefit. But actually, this wasn't the best optimization. This took a lot of work, like months, I don't know, 3-4 months to do it, and it wasn't the gain we expected. Why? Because we said, okay, let's try to optimize something. This is going to be needed. Just write it. We wrote it, but it wasn't very a targeted optimization. There are, I don't know, maybe code quality wasn't the biggest problem in performance. So writing a new compiler that improves code quality didn't change much. If you have, for example, a lookup that is really bad, then changing code quality is not going to improve your performance very much. So What else could we do for performance? There's one kind of thing that is called inverse lookup, which is the kind of thing that we had before the self-hosted kernel. We generated DLLs, and we generated a closure of the code. So we knew all methods that were going to be available in that DLL. So we could say, instead of doing lookup by traversing the method dictionaries, we can say, for this selector we have these implementers. So just check which of the implementer is, or send does not understand. So this is called inverse lookup. It's cool, but the only problem with the self-hosted kernel is that it's difficult to grow that, because you usually write assembly code for all the checks, but if you add a new method because you load the library or whatever, then you have to modify that code, and modifying the code could be difficult. You may need to load the assembler, or you have a template of assembly code that you have to manipulate. So there's a little bit easier solution that is polymorphic inline cache, which is very similar, but you don't generate a global cache, a global inverse cache for all methods, but you do this cache, this little cache, at each send site. Okay, so you say, when you send a message, you send that to an object, you look for the compile method, and you patch the code to call the method you found. If you send the same method again, and the class check fails, then you say, okay, we are going to add a polymorphic inline cache at the send site, which is a small block of code, of assembly code, that checks the two different implementations, and if it finds one of them, it jumps directly to the method, and if it doesn't, it does regular lookup and adds another entry to the cache. So some send sites are polymorphic, and these are the send sites we are looking at. It's like around 10%, but if you think that our lookup is very, very slow because we are doing linear lookup, we never replaced the linear lookup. We left it. We are still using linear lookup. So if we have 10% of polymorphic sites, we don't want to do lookup. Actually, slow lookups are not going to be issued because you have a polymorphic send site, because you are going to go to the global cache before that. So most of the time, even if you fail with a monomorphic inline cache, you are not going to go to the slow path. You are just going to do the global cache lookup. But it's even that is slow. So we implemented that polymorphic inline cache. For example, we can see how the lookup changed. It's very similar to what we had before. We have now, instead of doing lookup, we do cache lookup. So we are going to look in the global table. Then we are going to prepare the method for execution and create a new stub. You can't read? We are going to create a new stub for this send site and patch the call site. Okay? This is the case when we have failed in the monomorphic inline cache. I mean, the first time you do regular lookup, the second time you fail the monomorphic inline cache, and you say this is a polymorphic send site, just patch the call site. So, suspense, not waste. So, how fast did we get? Originally we were 700 times slower, or 2000. Now we are even faster at some benchmarks. Tiny benchmarks, we are 20% faster. You have to think that we are not doing GC now, so this 20% might go away. But we are even if we are the same. Actually, tiny benchmark is a crappy benchmark, so it doesn't measure anything. But we are even 10% slow in slopstone. This is a custom slopstone. For example, our array allocation is like 2 times slower than in the host VM, and still in smopstone we are 2 times slower than the host VM. But this is an amazing result. And so our conclusions. Our first conclusion is something that we didn't know when we started. We can match the host VM, okay, and there are many optimizations to do yet, and so we are reaching that performance. The optimization should be really carefully directed. That's something we learned with the optimizing compiler, and we are in a moment that we are finally hitting the wall of the hardware, because until now all problems were like optimizing some kind of code that was just a bad algorithm. I don't know, calling a method that could be sending a message that was not correct because there was another message that could be sent and could be faster. Okay, but now we are starting to hit hardware bottlenecks. For example, before coming here, I was trying to optimize float allocation, and float allocation was like 4 times slower than in the host VM, and the other kinds of allocations were faster. So I said, why is it so slow? I profiled it with an assembly profiler, and I found out that the problem was that I was calculating the amount of bytes that I needed to allocate the float, and to calculate that I was doing a division by 4 because I don't know why I had to pad or something like that. So I was dividing by 4, and I was using the IDIV instruction of Intel, and I looked in the manual, and that instruction in Haswell takes like 30 clock cycles. I mean, I would have never imagined that kind of things would be a problem now. It didn't happen before. When we implemented the compiler, this optimizing compiler, changing the quality of the code, like doing, I don't know, value numbering or different kind of algebraic optimization didn't change anything. And now, changing a division, changing it by a shift, changed a lot. So the benchmark became almost the same than the host VM. So another kind of thing that we learned is that now I'm working on the assembly kind of the project, but even doing improvements to the image is going to result in kernel improvements in terms of performance. So the only bad thing we have now is that we have all these cache placed in many places, and our virtual machine B was multi-thread able. So we were able to run multiple native threads. Now we have to do some some work to make for example, the polymorphic inline cache thread safe, or I don't know. The global cache was already thread safe, but this polymorphic inline cache is not. So we should see. To finish, we are working on optimization. We are now going to work on GC because we are at a good performance level, and starting to plug the browsers, debugger, and also we want to be able to control the little thing with a remote control. And well, then after, not so far, I don't know when, maybe. But that's all. So thank you very much. Any questions? Want to go? Leave now? Yeah.
calculation for all that work. So, I want to know architecture, which has run for.
Yeah, actually, it's running on Intel only, 32 bits. We would like to. Also, it's running only on Windows, but we work over Wine, so we work on Linux. And via Wine, and also in Mac. But we would like to port, but it's like much work. And Wine works great.
And the other, the motivation, what's the stress? What's the main drive to do it most? What is this?
Yeah, we want to bring. Okay, there are many goals, but I think the most interesting one is that we are breaking the wall, the difference between a virtual machine programmer and a standard programmer, if you want. So anybody can take some method, analyze lookup, and say, okay, I have a better algorithm. Just try it. Okay, you can. You don't have to do anything. You don't have to work with makefiles, compilers outside. All the work you do, you are going to do it with Moto. So I think it's one of the best. And it's dynamic. You can't change anything. Not yet, because we don't have browsers inside the running environment, but you're going to be able to change anything you want. Anything.